My name is Melissa, and in this video for Lab 2, we will discuss the motion of a falling object using 3 different methods. 1 by using a real-life example, and 2 by using a computer modeling program. In this computer program, we'll look at an object falling with only the impact of gravity, and then also look at it with only the impacts of gravity and drag force. So in this lab, I'll explain the problem, which is why the graphs with gravity and drag force are basically the same, and why the result of this experiment, which is drag force does not have a major impact, is not intuitive to some at first. In addition, in this experiment, drag force, which is a resistance force caused by the object moving through the air, is always going to be opposite in direction to that of gravity. Now let's watch the video of the object bread falling. In this video, the y-axis goes down. So as you can see, the dots are closer at first, which means the velocity was slower, and then it increased. So the time interval was kept the same, but yet the distance increased. However, close to the end, the distance was roughly the same, which means the velocity was the same. So now let's discuss the physics behind everything. So Newton's second law states that the final velocity is equal to the initial velocity plus the net force divided by mass times the change in time. In our case, the final velocity was greater than the initial velocity. We know this because the slope of a distance versus time graph is velocity. Here, the slope is less steep and it gets steeper. Therefore, the final velocity had to increase. However, so that means that net force had to increase, but a terminal velocity was reached, which means the net force roughly stayed the same. So this means that the drag force and the gravity force, they basically equaled each other out. Once again, we know that terminal velocity is reached when the velocity is constant. And roughly from 0.3 to 0.4 seconds, the slope of the graph is the same, which means the velocity was constant. Now we can briefly talk about the momentum principle. So momentum is mass times velocity, and then change in momentum is the net force times the time. And we know that a change in momentum occurred because there was a net force due to the fact that the object sped up and slowed down. Now let's talk about the computer code. So we had 2 codes. One of the codes was only gravity, and one was gravity and drag force. In both, the weight was the same, and the initial position was the same. This value was found via tracker software. In addition, I changed the time step to 0.01 in order to better correspond with the bread falling. Also, gravity was set to 9.8, which is constant, and this line basically says that the y-axis goes up. Once again, in both cases, the time had to be less than 0.402 in order to correspond with the bread falling. With the gravity and drag example, the gravity force was the ball's mass times gravity times this direction vector. In addition, the drag force was used, which was a constant times the magnitude squared of the velocity times that. And obviously the net force is the 2 added up. And in the just gravity case, it was the same exact thing, except we didn't have a drag force. So as you can note, the data does not predict the model. The 2 lines using data from the computer have a perfect parabola shape, while the observed motion doesn't. This is due to the fact that it was hard to pinpoint the center of mass with the blurs. However, outside from experimental errors, the graphs are different because of the small time interval. Because the fall was short, the drag force was very small. Finally, the B constant was small, 0.01. This was determined by guess and check, which greatly decreased the drag force. So in conclusion, with more distance covered, the graphs would be separate, with the model using gravity falling more distance. This is because it wouldn't have the impact of drag force. So in this what does it mean question, we have to say if any model predicts terminal velocity. Terminal velocity is where drag force equals gravity. Basically, there is zero acceleration. Therefore, let's look at this graph. Where the slope is steady, this has reached terminal velocity. In real life, we need a longer time interval to determine if it reached terminal velocity. But here, with the model with gravity and drag, the slope is roughly the same, which means the velocity is the same, which means it has reached terminal velocity. So if an object was thrown downward, the terminal velocity would be the same as if it was just dropped. However, the time would be different because the object thrown downward would have to slow down in order to reach zero acceleration. So in conclusion, although mass doesn't impact air resistance, the weight of the object can be much greater to overcome it. This is why the gravity played a main role in our example.